Right, before we begin towards the understanding of thermodynamic tables and recognize different tables uh, with regards to different areas in a PV or TV diagram, let us define a new property first, which is enthalpy. And before we begin understanding what enthalpy is, can someone recall what is energy associated with flowing fluid, or what are the components of energy associated with a flowing fluid?
So the potential energy of the fluid,
Yes,
the energy due to pressure changes,
energy due
और
to
the flow energy उसकी अपनी जो है kinetic energy.
yes. So we have essentially three kinds of energies: the potential energy, the kinetic energy, and the flow energy. And if you recall, you're familiar with potential energy of a fluid, which is dependent upon the elevation, kinetic energy is dependent upon the velocity, and flow energy is dependent upon the pressure. If you recall, we did a derivation based on flow energy, and we defined that if we have this control volume, the small amount of control volume having a pressure P and volume V, if this volume of fluid has to move into the material, there is a force that needs to be applied onto this control volume, and the force that would be applied onto this volume would be essentially equal to the pressure of the fluid multiplied by the cross-sectional area through which that force has to be applied, or the cross-sectional area through which that fluid has to move into the control volume. And if we want to convert this force into the work done by the fluid, which is work mechanical, this would essentially be equal to force multiplied by the length for which that force acts, which is essentially the length of this control volume. And if I plug in pressure into area instead of force multiplied by length, this term essentially becomes the volume. So PV is the mechanical work which is associated with the flowing fluid. And if I express this work per unit mass, W mechanical small, which is flow work, it would be pressure multiplied by the specific volume. This is what we have already learned in our chapter 2. And you have already seen this slide before. So now we want to relate the internal energy and enthalpy. So how do we do that? Before we try to establish a relationship between the two, we would recall that the flow work is essentially PV, pressure into control, pressure into volume, has the units of energy, joules or maybe kilojoules, and P specific volume has the units of kilojoules per kg. Again, it is associated with energy. Similarly, internal energy, which is defined by the capital letter U, has the units of energy, which is again joules or kilojoules, and internal energy per unit mass, it contains the units of kilojoules per kg or joules per kg. Now, whenever a fluid is entering into a control volume, it actually has these three components. It has its own internal energy, and it has its own um, flow energy. Similarly, when it is flowing out of the control volume, it would have the internal energy plus the flow energy. In order to make our analysis easier, we have combined these two energies, the internal energy and the flow energy, for the analysis of control volumes, and we have termed this combination of energies as enthalpy. So enthalpy is nothing but a combination property. In this case, it is basically internal energy combined by flow energy per unit mass gives rise to enthalpy, which is represented by small h for per unit mass and capital H for energy. All right,
Yes,
is
sir.
it clear?
Yes.
All right. Moving on, now we need to understand that what is the need of property tables? Why do we need to have these tables? For most substances, the relationship among thermodynamic properties are too complex to be expressed by simple equations. So The relationship between thermodynamic properties are not easy to be expressed in simple equations. Rather, uh, these properties are frequently represented in the form of tables so that you don't have to plug in the values and calculate yourself. This is one reason why you need tables. Number two, there are certain thermodynamic properties that can be measured easily and directly, but there are others that cannot be measured directly, and they are calculated based on a relationship between the measurable properties and the non-measurable properties. Fortunately enough, you don't have to perform the experiment, calculate, measure. These measurements or the measurable properties as well as the calculations based on these measurable properties for non-measurable properties. They are both presented in tables in a convenient format so that you don't have to perform neither the experiment to measure the measurable properties nor to perform calculations using complex equations to calculate the non-measurable properties. A list of tables. This is the list of tables that are given at the end of your book. First thing first, that you have two sets of the same table. If you see, you'll have table A1 and you will also have table A dash 1. Sorry, you'll also have a table uh, table A1E. Now, whenever you have the symbol E, this would represent the English units system. So you have the same table, table A1 or without E tables are basically the SI unit based tables, and the tables having E at the end are basically based on English unit system. Coming to the tables, the important tables from your point of view includes table A4, A5, A6, A7. They are basically dealing with saturated water temperature table, saturated water pressure table, superheated water, and compressed liquid water. So they are basically known as steam tables or water tables, in which you have all the three regions defined for you. If you remember this uh, temperature specific volume or pressure specific volume diagram, you have this dome. This region is superheated region, this is mixed region, and this is compressed liquid region. You have table A7 for compressed liquid, table A6 for superheated, and table A4 and A5 are basically for mixed region, and this is in the case of water. When you have a different refrigerant, let's say R134A, which is a refrigerant used in refrigeration cycles, you have different tables. The table A11, A12, they are temperature and pressure table for saturated refrigerant, that is the mixed region, and table A13 is for the superheated region. Similarly, you also have tables for ideal gas properties. Ideal gas properties of air, table A17 is the most frequently used tables in terms of ideal gas properties. Then you have also the tables of ideal gas properties of nitrogen, oxygen, carbon dioxide, carbon monoxide, hydrogen, water, monatomic oxygen, hydroxyl group. So these are ideal gas properties. Now, you may not be using all of these tables very frequently, but probably table A17 would be used very frequently. Table A4 to A7 would be used very frequently, and we'll try to understand the tables A4 to A17, A4 to A7, and the similar pattern would be followed in understanding the tables A11 to A13. So we'll go through table A4 to A7, and the same methodology of analysis would be applied to A11 to A13 also. Let us begin with the table A4 and A5. Table A4 is basically saturation properties of water under temperature, and table A5 is saturation properties of water under pressure. Now, if I place a line over here, you don't need to worry about this side at the moment. The difference between A4 and A5 is in the first two columns. If you look at table A4, the first column is of temperature and the second column is of saturation pressure. So if you have been given the value of temperature and you want to find out the saturation pressure, you will go to table A4. In table A5, if you in the first column is of pressure and the second column is of T saturation. So if you want to find out the saturation temperature for a specific pressure, you will go to table A5. Clear so far?
Yes, sir.
All right. Now the next column is of specific volume. This column is same. The rest of the columns are same for A4 and A5. The values may not be the same, but the column headings are the same. Specific volume, the first column is given for saturated liquid and the second column is given for saturated vapor. Now remember, saturated liquid is being recognized by the subscript F and saturated vapor is being represented by the subscript G. So anywhere if you see the subscript F, you will recognize that you are referring to saturated liquid. And anywhere if you see the subscript G, you are basically referring to saturated vapor. If you remember the TV diagram, let's say we have this temperature volume diagram, this is the dome, and you have some pressure, constant pressure that you are referring to, let's say P1. This point refers to saturated liquid, which is defined by Vf, and this point refers to saturated vapor, which is referred by point Vg. I hope this is clear.
Yes, sir.
All right. So let's say if I'm talking about 85 degrees centigrade, at 85 degrees centigrade, my saturation pressure or the pressure at which boiling would take place would be this. The boiling, when once it starts, that means the saturated liquid state, the specific volume this of the liquid, 100% liquid phase, and saturated vapor, once it converts into vapors, 100% vapors would have specific volume of 2.2861. That's how these values are being assessed. Now let's say I have let's say I have this PV diagram and my system is a system in which the temperature is 90 degrees centigrade and I know that I am at saturated liquid. I need to find out the pressure corresponding to this system and the specific volume corresponding to this system. So how would I find it out? Which table should I go to?
A4. So temperature.
I'll go to the table A4, find out the temperature where it says 90 degrees centigrade. The pressure corresponding to 90 degrees centigrade, the saturation pressure would be 70.183. This would be the pressure of this line and also the pressure of my system. The system would be at pressure of 70.183 kilopascal. And what would be the specific volume of the system?
So liquid phase में
Zero
0.101.
point zero one.
So this would be the specific volume of my system since it is in the saturated liquid condition at the moment. Now, the term Vf basically means specific volume of saturated liquid, Vg means specific volume of saturated liquid, saturated vapor, and Vfg is a term which is used to express the difference between specific volumes of saturated vapor and saturated liquid. Similarly, UFG over here, it is representing the difference between the internal energy of saturated vapor and the difference between the internal energy of saturated vapor and the saturated liquid. So These values are basically not for 90 degrees centigrade. These are not for 90 degrees centigrade. Maybe they are for 100 degrees centigrade. So don't confuse yourself. This UF, UG, and UFG, they are for 90 degrees centigrade. Similarly, HF, HG, and HFG are for 90 degrees centigrade. And this HFG, which is 2659.6, uh, sorry, HFG 2282.5. This value HFG is basically the latent heat of vaporization. It is basically the amount needed to vaporize a unit mass of saturated liquid at a given temperature and pressure. All right. So at 90 degrees centigrade and 970.8183 kilopascal, you require 22 to 2282.5 kilojoules per kg of energy to convert saturated liquid into saturated vapor. So far, is it clear?
Excuse me सर,
Yes,
ये
sir.
टेबल्स
सर ये constraint है।
एल्टीट्यूड पे
Sorry,
डिपेंड नहीं करेंगे?
जी,
एक्सक्यूज मी सर, ये टेबल्स हाइट पे डिपेंड नहीं करेंगे
हाइट पे डिपेंड नहीं करेंगे।
सर? क्योंकि प्रेशर तो हाइट से वेरी करता है, तो ये तो वेरी मतलब इंडिपेंडेंट है ना सर हाइट से?
बेटा प्रेशर हाइट से वेरी करता है तो टेम्परेचर वेरी नहीं करेगा। मतलब आई मीन व्हाट इज द सेंस विद इट? हाइट के साथ क्या ताल्लुक है इसका?
सर ये उधर चला गया वो
कंफर्म
जी
करना चाह
फ्लूइड
रहा था।
मैकेनिक्स साइड।
जी सॉरी।
ये फ्लूइड मैकेनिक्स वाली साइड पे चला गया सर।
नहीं नहीं, let him go anywhere where he wants to, but what is the connection between pressure and height and pressure and temperature? अगर मैं कहूँ, let's say if I say that at 1 atmospheric water boils at 100 degrees centigrade, does it matter whether I am sitting uh, at Karachi or Lahore or Rawalpindi, wherever I am sitting? Does it matter?
नो सर, सर आई गॉट इट,
All right,
थैंक यू सर।
you're welcome. So, with height, your pressure would vary, yes, but if the pressure would vary, your boiling temperature would automatically change. So it has nothing to do with the height. Anyways, so far the table A4 is clear to you?
यस सर।
यस।
All right. Moving on, we have saturation properties of water under pressure table. This is a table where we are expressing the values under pressure. So as I specified in this table, the first column would be of pressure and the second column would be of saturation temperature. So now I am expressing saturation temperature in regards to specific pressure. Now, if I want to find out, let's say I have a system which says that I am at saturated vapor state. This is the state of my system. My system is at saturated vapor and the pressure in the system is 350 kilopascal. Now, can you find out the saturation temperature and specific volume of the system?
यस
How?
सर, जो प्रेशर वाला टेबल है उसको उस पे जाएंगे और
ठीक है।
350 जब हमें प्रेशर जो दिया हुआ है
हम्म।
उस कॉरस्पॉन्डिंग वैल्यूज देख लेंगे।
Very good. So you you'll go to the pressure value of 350 kilopascal and you will read the temperatures just next to it, which is the saturation temperature. So this line, which is a constant temperature line, would be at 138.86, or the saturation temperature, this temperature would be 138.86, and the specific volume would be 0.001079. This would be the specific volume of saturated vapor. Is it so?
सर लिक्विड काम नहीं कर रही है।
So, yes, this would be the specific volume of saturated vapor as represented by Vg. Clear enough?
यस सर।
यस सर।
All right, great. Now, so far we have looked at the cases where you are setting on either this line, which is the saturated liquid line, or on this line, which is the saturated vapor line. In case you are somewhere in between this region, in case you have a mixture of saturated liquid and saturated vapor, how do you assess the properties in such a condition? In a condition where you have a mixture of saturated liquid and saturated vapor, uh, which is probably which happens during the vaporization process, you have to analyze the mixture properly, and for that you need to know the proportions of saturated liquid and saturated vapor phases in the mixture, that how much is saturated vapor and how much is saturated liquid. This is uh, an information that is required to assess the property of the mixtures. In order to do so, you define a new property which is termed as quality and defined by the symbol X, and it is the ratio of mass of vapor or saturated vapor to the total mass of the mixture. So it is nothing but mg, which is the mass of saturated vapor, divided by mt, which is the total mass of the mixture. Clear?
Yes, sir.
Now, if I say I am standing, if I am standing, let's say this point over here is point 1, this point over here is point 2, and I am standing at point 1. At point 1, at point 1, what would be the mass of uh, saturated vapor?
Zero.
All right, it would be 0. So what would be the value of x?
Zero ही होगी.
X would be 0. Very good. Number 2, if I'm standing at point 2, what is the mass of vapor with regards to the total mass?
तो वहाँ mass of vapor की कोई value होगी और mass of liquid की value नहीं होगी.
टोटल मास के पॉइंट ऑफ व्यू से क्या वैल्यू होगी मास ऑफ वेपर की?
टोटल मास की जितनी भी वैल्यू की
Total mass equal ही
वेपर
होगा.
की वेपर की
सॉरी
वैल्यू
सॉरी
टोटल मास की जितनी भी वैल्यू होगी वो वेपर की वैल्यू होगी.
एक्स की वैल्यू क्या हो जाएगी?
1.
Alright, x equals to 1. So now you know that the minimum value of x, which is quality, could be 0, which represents saturated liquid, and the maximum value of x could be 1, which represents saturated vapor. Alright?
Yes, sir.
Great. Again, mass of vapor divided by the total mass, and this could be expressed in a way that you have mass of liquid plus mass of vapor, which is represented by mf, which is representing saturated liquid, and mg, which is representing saturated vapor. Now, quality is between 0 and 1, 0 for saturated liquid and 1 for saturated vapor. There's one more thing, that the properties of the saturated liquid are the same whether it exists alone or it exists with a mixture of saturated vapor. Do you understand this point?
तो दोबारा बता दें.
All right. It means, let's say I take a property internal energy. I have x equals to 0. That means I am having saturated liquid. All of this container contains saturated liquid, and internal energy of this saturated liquid is UF. All right.
Yes, sir.
Now I have another state where x equals to 1, and I have saturated vapor, and my internal energy value is UG. Clear enough? Same volumes.
Yes, sir.
Let's say I have a mixture in which I have 30% saturated liquid and 70% saturated vapor. What would be the internal energy of this system? I'll call the internal U average would be dependent upon UF and UG. It means that the saturated liquid, this portion, this portion would have the internal energy as UF, and this 70% portion, this portion would have the internal energy as UG, and the total mixture this would have. So first thing, the properties of saturated liquid, the property of saturated liquid is internal energy. It would be UF over here, it would also be UF over here, but the contribution of saturated liquid would be now zero point 0.3 or 30%. So zero point 0.3 UF plus zero point 0.7 UG would give me the average value. All right. It would be the property of saturated liquid would remain the same. Only its contribution towards the internal energy of the mixture would change. All right.
Yes, sir.
All right, moving on, let's see how we can develop a relationship for the average properties of the mixture. You have a mixture which contains saturated vapor and saturated liquid. Both have their own specific volumes. In case of mixture, the mixture would have an average value. How can we find out or how can we develop a relationship for the average value? Let's see. So consider a tank that contains saturated liquid and vapor mixture. The volume occupied by saturated liquid would be Vf, and the volume occupied by saturated liquid would be capital V subscript G. The total volume would be the summation of the two volumes. That means the total volume of your system would be volume of saturated liquid plus volume of saturated vapor. And I can express any volume, I can express it in terms of mass multiplied by a specific volume could be used to express volume. So I'll replace these volumes with mass multiplied by specific volumes. So the total volume would become total mass MT multiplied by the average value of the mixtures, average specific volume of the mixture. Similarly, the volume of saturated liquid would convert into mass of saturated liquid multiplied by the specific volume of saturated liquid, and volume of saturated vapor would convert into mass of vapor multiplied by the specific volume of the saturated vapor. So far, is it clear?
Yes, sir.
All right. Now, if I divide all of this, both sides, with total mass, I would have essentially V average is equal to, or before that, I know that mass of saturated liquid, which is MF, is essentially equal to MT minus Mg, total mass minus the mass of vapors. So I can write this expression in this way, that the MT average is essentially equal to MT minus MVF plus MGVF. Is it clear?
Yes, sir.
All right.
सर ये
Now,
दोबारा एक्सप्लेन कर दें वन टाइम.
क्या चीज एग्जैक्टली बताएं, क्या रिप्लेस दोबारा
सर
रिपीट करना है?
MT माइनस MG सर ये.
All right. What is written over here? ये क्या लिखा हुआ है?
MS MSV.
MF is essentially what? Mass of saturated liquid,
Yes, sir.
which is
Yes,
equal
sir.
to total mass minus mass of saturated vapor. So you have just plugged in it over here.
Okay, sir.
Clear?
Got it. Yes, sir.
All right. Now if I divide the whole equation with total mass, so this would cancel out and I would have V average, specific volume average. This would cancel out and I will have 1 minus mg over m total multiplied by specific volume Vf plus mg over mt into specific volume Vg. Is it clear?
Yes, sir.
And by definition, you know x is equivalent to mg over.
Empty.
So I can replace V average equal to 1 minus x Vf plus x Vg. Clear enough?
Yes, sir.
All right. Now, if I open up this bracket, I would essentially have Vf minus x Vf plus x Vg. Clear enough?
Yes, sir.
And I can make x as the subject of the formula and write down Vg minus Vf in the bracket. Clear?
जी सर.
And Vg minus Vf क्या होता है?
VGF.
वो evaporation वाला था
Vfg. All right. So you will have this expression with you. You'll have this expression with you where you can write Vf plus x Vfg. So if I summarize it, you'll have this expression for average value. That means average value is Vf plus x multiplied by the difference between the saturated vapor and saturated liquid. Clear enough?
Yes, sir.
Now, if I rewrite this equation over here, I can write it as, if I make x as the subject of the formula, I can write it as V average minus Vf over Vfg. This is how I can express x. We would like to see how would uh, this appear on the PV diagram on an isothermal temperature transformation line. How would x appear? Let's see. Let's say this is the formula. I'll write it again for you. X equals to V average minus Vf over Vfg. This is the formula. Now, if I have temperature specific volume plot over here, this is the temperature specific volume plot, and this is the isothermal line, the phase transformation line. Over here, I have this is, let's say, Vf, this is Vg, and I have my mixture somewhere over here. Let's say I'm assuming it. So this mixture would have the value of V average. I represent the saturated liquid as A, the V average value as B, and the Vg value as C. Now, in terms of X, can you tell me how can we express this V average minus Vf? What is this distance on this line?
Sir,
AB,
from B to
Sorry,
sir, distance
AB,
from
Distance AB.
there's someone. I am not able to hear him. What are you saying? Someone was saying something.
Sir, the distance from B to C point is the
From
distance.
B to C would be V average minus VF.
Yes, sir.
V average is this value. VF is this value. V average minus VF would be B to C or A to B?
A to B, sir.
A to B. And what would be the distance VFG?
A to C? No, sir. C to C.
VFG is what?
Sir, C to A.
C to A or A to C is the same thing. So essentially, you are referring to X as this distance divided by the total distance. All right.
Yes, sir.
So you are referring to X as this blue distance divided by the uh, total red distance A to C. Now, if I say X equals to zero point 0.5, where do you think the point should be?
The half rate
Center.
between AC.
Exactly in the center. All right.
Yes,
And X equals to zero point 0.2. It should be close to A or C?
close to
A.
A.
Close to A, somewhere over here. And zero point 0.2 means 2 over 10. So if you physically see, mass of vapor is less as compared to the total mass. Clear enough? So you're getting the physical understanding of what is meant by X as in comparison to the position, its position on line.
Yes, sir.
All right, great. So there's the same thing explained over here. Again, I'll not repeat it over and over again. The same relationship V average would be applied for all the rest of the properties. The enthalpy value and average enthalpy and average internal energy would vary the same way. That means the UF value plus X multiplied by UFG. Similarly, HF value multiplied by X multiplied by HFG, all the values would have the same relationship. The values for the mixture. And what do you think that the what would the average value of a mixture, any average value, whether it's internal energy, enthalpy, or its specific volume, should it be greater than that of saturated liquid?
Yes, sir.
No,
G?
sir.
Yes, sir.
No, sir.
Who says
Saturated
no?
liquid.
No कौन कह रहा है? Who is saying no?
सर ग्रेटर होगी क्योंकि वो एडिशन हो रही है ना.
Can you repeat it again?
सर ग्रेटर होगी क्योंकि वो एडिशन हो रही है.
जी बिल्कुल. दी वैल्यू, एवरेज वैल्यू में यूएफ तो ऑलरेडी एडेड है, तो यूएफ से ज्यादा ही हो सकती है, उससे कम तो नहीं हो सकती. इज इट क्लियर?
Yes, sir.
ऑलराइट. एंड शुड इट बी ग्रेटर देन the value of VG?
No, sir.
No, sir.
Obviously, if you see physically on the plot also, average value would lie in between these two maximum values. VF and VG, average value of the mixture would lie somewhere in between. Clear enough?
Yes, sir.
Is it clear?
Yes, sir.
All right. Now, so we say that if your specific volume or your, let's say, internal energy or enthalpy values, if it is greater than, let's say, that of saturated liquid and less than that of saturated vapor, I am in which region?
जहाँ पे दोनों मिक्सचर एग्जिस्ट कर रहा है उनका।
Very good. And if these values are, let's say, my specific volume is less than Vf, I am in which region?
So liquid phase.
Very good. I am in compressed liquid region. And if it is greater than Vg, I am in
Vapor.
superheated region.
Right.
Clear?
Yes, sir.
All right, because you would have to identify yourself that which region are you in based on the values and the table. So you'll compare with the table and you'll identify the regions yourself. So you should have an understanding based on the values whether you're lying in saturated liquid, saturated vapor mixture, or in compressed liquid or superheated region, which region you're lying in. The same thing over here. Now, for calculations of mixtures, when you are in mixed region, you only need table A4 and A5 along with the property of mixture, that what is the value of X, or some information that relates to the value of X. That is only needed to calculate the properties of the mixtures. But when you go to superheated vapor region, in superheated vapor region, the first thing is to identify whether you are in superheated vapor region or not. What are the conditions that or what are the uh, properties that identify that you are in the superheated vapor region? These are the characteristics of superheated vapor region. We'll look at them one by one. The last three are the simple one. So let's start with the last three. It says if your specific volume is greater than of saturated vapor, if your internal energy is greater than of saturated vapor, and if your enthalpy is greater than saturated vapor, any one of them, at a given pressure or temperature, you are basically in superheated vapor region. Is this point clear to you?
Yes, sir.
Great. Now let's look at this first, low pressures at a given temperature. Look at pressure specific volume plot. Pressure specific volume plot for a constant temperature, T1 line, the dotted line which is at the bottom, this line. So for a constant temperature, pressure is which pressure?
तो जो कन्वर्जन के लिए जो प्रेशर चाहिए होता है बॉइलिंग वाला।
Which is known as the saturation pressure. All right.
Yes, sir.
So this pressure is saturation pressure. Now, if my pressure is less than saturation pressure on this line T1, I'll be where? Above P saturation or below P saturation?
Below
Below
P saturation.
saturation.
Sorry.
Below P
Below.
saturation.
So I'll be, let's say I am somewhere over here. My pressure is less than P saturation for the constant temperature. I am in which region?
Superheated vapor region.
So you see, if your pressure is less than P saturation at a given temperature, you are basically in superheated vapor region. Clear enough?
Yes, sir.
Similarly, if you are on temperature specific volume plot and your pressure is constant, let's say your pressure is P1, this bottom line, this line, you are on this line. What is this temperature? T saturation.
Yes, sir.
So for this pressure P1, if my temperature is greater than T saturation, I am in which region?
Superheated vapor region.
Superheated vapor region. Clear enough? All these conditions are clear to you?
Yes, sir.
So now you can identify if pressure is given to you or temperature is given to you, two properties are given to you, you will identify your corresponding region and then you will go to the corresponding table, which is table A6 for superheated vapor. Now let's see how the table in superheated vapor works. In superheated case, you have basically the tables in this form where the first column is of temperature and over here there is a box which incorporates the pressure and in the bracket there is a temperature written. All right, so you'll have different pressures, and for each pressure you will have the same block. You will have the first column of temperature, and you will have then the properties written next to them. Clear enough?
Yes, sir.
All right. So now the pressure written in the bracket is the saturation temperature for the corresponding pressure. For instance, I have this temperature specific volume plot, and I say that my pressure line is zero point 0.5 megapascal. So for zero point 0.5 megapascal, I have this table over here. I'll go to the table which says zero point 0.5 megapascal, and the temperature written in the bracket, this temperature is basically my saturation temperature. So 151 is my saturation. All right,
Yes, sir.
great. In every column, the first row would be that of properties belonging to saturation temperature and corresponding to this point, which is saturated vapor. Clear enough?
Yes, sir.
Great. Now let's say that I have been given the information that this is my system. My system is at zero point 0.5 megapascal pressure, and the temperature of my system is 250 degrees centigrade. Where am I in this table?
जिस टेबल में 0.5 पास्कल प्रेशर लिखा होगा
Which region am I
उस
in?
yes sir
Sorry, which region? First identify the region. This temperature is 151.83. The system is at 250
super
degrees
heated
centigrade. So which region am I in?
Superheat.
Superheated region. So I'll go to table A6. I'll read out the pressure, which is zero point 0.5 megapascal, and I will go to the temperature which says 250 degrees centigrade. This line or this row would correspond to my properties. So I have, I'm over here. This is 250 degrees centigrade. Now, if I want to find out the specific volume of my system, my specific volume of the system would be what?
0.47443
Very good. So represented by V1, I have given it a variable. This is 0.47443. And if you see the specific volume for saturated vapor, which is this point Vg, it is corresponding to the saturated temperature. Clear?
yes sir
So my specific volume would be greater than the saturated vapor specific volume. I hope it is clear.
yes sir
All right. Now moving on to compressed liquid table. Compressed G.
सर ये लास्ट पॉइंट नहीं क्लियर हुआ ये जो 0.3 वाली वैल्यू है
All right. The values where it is written saturated. For example, this is written saturated, or this is written saturated. Under temperature column, the first row would be of saturated temperature. For saturated temperatures, the values which are written, these three values, they correspond to this saturated vapor point. All right.
yes
Clear?
यस सर
क्लियर
ठीक
हुआ
है
या नहीं हुआ?
जी
जी,
जी सर क्लियर
जो
जी सर
लाइन
क्लियर
6
है
टेबल के अंदर कोई भी प्रेशर, ऑलराइट, इसमें जो पहली रो होगी वो सैचुरेटेड टेम्परेचर के कॉरस्पॉन्डिंग, सैचुरेटेड टेम्परेचर के कॉरस्पॉन्डिंग दो वैल्यूज हो सकती हैं, या वो वैल्यू हो सकती है या वो वैल्यू हो सकती है सैचुरेटेड वेपर की या सैचुरेटेड लिक्विड की। लेकिन सुपर हीटेड टेबल में जो सैचुरेटेड टेम्परेचर के कॉरस्पॉन्डिंग वैल्यूज होंगी वो सैचुरेटेड वेपर के लिए होंगी। ऑलराइट,
यस सर
moving on to compressed liquid table A7. Again, you have to identify the region for yourself. How would you identify? There are certain conditions, the same conditions. these are the conditions. These three conditions are known to you, that enthalpy should be less than saturated liquid enthalpy, internal energy less than saturated liquid internal energy, specific volume less than saturated liquid specific volume. Similarly, temperature would be less than T saturated for a given pressure, and pressure would be greater than P saturation for a given temperature. Clear enough? These things are clear to you? Exactly the opposite of superheat vapor.
Yes, sir.
All right. Now, for compressed liquid, normally the tables are not that extensive, and you normally approximate the values of compressed liquid system. The reason is that for the compressed liquid, properties are much more dependent on temperature than they are dependent on the pressure itself. For instance, I say that the specific volume of liquid, if I am at 1 atmospheric, let's say my temperature is 20 degrees centigrade or 25 degrees centigrade, and I increase the pressure from from 1 atmospheric to 100 atmospheric, pressure मैंने 100 times बढ़ा दिया है, the effect on a specific volume would be negligible. All right. However, if I say that if I increase the temperature from 25 degrees to 50 degrees centigrade, the change in specific volume would be significant. So compressed liquids or liquids are basically not that much sensitive to pressure as they are to temperature. So how do you approximate these properties? You approximate a compressed liquid as saturated liquid for the given temperature. For example, you have been given a system where the temperature is 80 degrees centigrade and pressure is 5 megapascal. That means you are standing at this point. This is 5 megapascal line. This line is 5 megapascal line. And at 80 degrees centigrade, you are in compressed liquid region. Now, if I go to table A7, I don't find the data of 5 megapascal. What should I do? I don't have the tabulated data for that. I would use an approximation and I would shift this point to saturated liquid point at 80 degrees centigrade. So I'll go to table A4, I'll go to 80 degrees centigrade and I'll read out the value of, sorry, I'll go to table A5. I'll go to table A5 and I'll see where the saturation temperature is 80 degrees centigrade. I'll read out the value of UF. Clear?
Yes, sir.
All right. So all the properties, whether it is specific volume, whether it is internal energy, or whether it is enthalpy, for compressed liquid, they can be expressed as the saturated liquid value at the given temperature, disregarding the pressure. For example, if I take this liquid as saturated liquid at 80 degrees centigrade, the pressure corresponding to this line would be, let's say, some different pressure, 2 megapascal. So I'll ignore the pressure. I'll just take the temperature as my reference and I'll measure the value of saturated liquid at that temperature. So all the three values, whether it is specific volume, internal energy, or enthalpy, they can be approximated as saturated liquid values at the given temperature. I hope this is clear up till now.
Yes, sir.
All right. So what you can do is that you can, for enthalpy, there is a more accurate approximation that can be used. You can use this approximation also, but at times, if you want to have a more accurate approximation, you can use this approximation where the first term is the same thing. The first term, this is H equals to HF at temperature, saturated liquid at temperature. It is the same thing. The difference is this term. This term is the different term. It says that you will add the specific volume into delta P. Which specific volume? Specific volume of saturated liquid at this temperature multiplied by the pressure which is difference in the pressure which is given to you and the pressure of the saturation pressure at this given temperature. So you have 2 megapascal and 5 megapascal. You will take the saturated liquid multiplied by 5 minus 2, which would be 3. And this additional term would give you a more accurate approximation. Clear enough? So what I'll do is that I'll stop over here, have